Our eyes intuitively assign instantaneous slopes to individual points on plots of functions. At a simple level, we might define slope as the ratio of the change in height of a plot of a function relative to an underlying change in horizontal location. However, there is no change in the value of a plotted curve at any single point. At any single point, there is only one value, no change. How can we resolve this apparent intuitive conflict? The concept of a derivative uses a limiting process to bridge the idea, on the one hand, of a slope seemingly belonging to a single point, with the idea, on the other hand, of evaluating slope by comparing multiple points separated by finite distances. This slide deck is divided into 5 videos. In this first video, we will define the derivative and discuss symbols called differentials. The purpose of the remaining 4 videos is to begin to build a table of rules that will allow us to analyze slopes, meaning rates of change, for a variety of functions. The examples we will study will be the power rule, the chain rule, the product and quotient rules, and the rules for calculating the derivatives of sine and cosine. The understanding that we will develop will provide a foundation for the analysis of a variety of biological systems. These include the dynamics of expanding cell populations, the abundances of biological molecules involved in chemical reactions, and oscillations in biological circuits. We begin by defining the derivative. Sir Isaac Newton on the left and Gottfried Leibniz on the right are commonly considered the founders of differential calculus, which is, crudely speaking, a study of instantaneous slopes. Consider a function with plot f on x versus x. The function associates the point x equals x naught with f on x naught and associates the point x naught plus delta x with f on x naught plus delta x. Draw a right triangle with legs parallel to the horizontal and vertical axes with lengths delta x and delta f respectively. The rise over run is delta f divided by delta x evaluated, and that's what that vertical bar means, evaluated, when the left-hand corner of the triangle is planted at x equals x naught. This is the difference between f evaluated at x naught plus delta x and f evaluated at x naught, that vertical height divided by the length of the horizontal run delta x. The value that we obtain by calculating the rise over run depends on the function under study, depends on the location x equals x naught where we plant the left-hand corner of the triangle, and depends on the horizontal length delta x over which we allow the function to vary. We can get different numerical values for rise over run by, for example, considering values of delta x alternative to the length initially plotted. In this cartoon, the ratio rise over run appears to approach a limiting value that we can determine by considering an unending succession of calculations with smaller and smaller but all the while finite values of delta x. This is red, the limit as delta x approaches 0 of the ratio f on x naught plus delta x minus f on x naught all over delta x. This is the definition of the symbol df dx evaluated at x equals x naught. We call this the derivative of f on x versus x evaluated at x equals x naught. This definition formalizes a notion of an instantaneous slope at x equals x naught. When we determine the derivative of f on x versus x, we say we are differentiating f on x with respect to x. The symbol for the derivative includes a piece df and a piece dx. These are called differentials. Even though differentials are notated to look like individual quantities, almost like differences delta f and delta x, it is important to remember that differentials are not numbers. In this course, we will regard differentials as syllabic components that are said to be part of meaningful contexts only when paired with other syllables to form words. As an example, the pattern df by itself is meaningless, but when written over a bar over another differential syllable dx, the result is an entire fraction-looking symbol pronounced as the one unit df dx, which as a whole has meaning as the derivative of f with respect to x. We will learn later that the syllable df can also be part of a meaningful structure when paired with another syllable, the smooth s, which looks like a sound hole on a violin. Again, in this course, we regard isolated differentials as no more meaningful than isolated syllables torn out from words. Paired appearances of the symbols df and dx, such as in df-dx, refer to an unending process of studying successively shrunken, but all the while finite, numbers delta x, with a corresponding collection of numbers delta f, which themselves could be finite or zero. Think of differentials as shorthand for limiting processes rather than as literal numbers. Here is one example of a finite number delta f and a finite number delta x. As we explore smaller but always finite horizontal separations delta x, we enumerate other numbers delta f. If the ratio of the number delta f to the number delta x becomes arbitrarily close to a limiting number, then that limiting number, which no delta f over delta x necessarily ever achieves, is called df dx. The appearance of differentials in pairs helps us to keep in mind a notion of paired shrinkage of finite quantities. If you find a line of derivation in calculus apparently notating df on its own, then look around nearby for a corresponding symbol that looks like dx, or at least for an implied notion of paired shrinkage. Regardless of how closely we look, at least in this course, we find no tick marks on the number line corresponding to df or to dx. Differentials are not numbers. Because derivatives and differentials refer to limiting processes, understanding properties of limits is helpful for understanding derivatives. In the slide deck on limits, we learned that limits do not always exist. This is one example of a property of limits that carries over to derivatives. Derivatives do not always exist. To illustrate this point, we sketch an example of a plot that jiggles wildly. It looks jagged even when we zoom in to magnify small regions. We can choose to identify these 2 points, separated by this finite horizontal run, and then draw this right triangle to calculate a rise over run. We are also allowed to choose other locations for the yellow marker. Some of the ratios of rise over run calculated using these intermediate points might be similar to the rise over run of the triangle outlined in turquoise, but some ratios of rise over run might be very steep and others very shallow. Even as the horizontal separation between the red and yellow markers becomes arbitrarily small, the ratios of rise over run explored continue to fluctuate wildly. They do not settle down to a well-defined single slope. This is an example of a function whose plot everywhere has no slope. We don't mean to say that the plot has everywhere zero slope. We mean instead that the plot has everywhere no meaningful value of slope, not even the value 0. In this video, we discussed differentials and the potential non-existence of derivatives. Understanding these details allows us to avoid conceptual roadblocks when using the concept of the derivative that we defined. Now that we have established basic familiarity with the idea of a derivative, we can apply it to derive a set of rules that will help us to analyze the slopes, meaning the rates of change, of a variety of functions. The power rule is the example that we will study in the following video.